Hey guys, so something exciting that you might notice right now. My lighting is so much better. I got one of those little ring lights that's supposed to help with your lighting, so now you can actually see my face. So there's a little bit of a glare right here on the TV. If that's really annoying, tell me and I'll figure something else out. This is the best way that I could do this, that you could still see my face actually pretty well, but that the glare wasn't somewhere that you needed to see something. So today, solids of revolution. So a solid of revolution is the shaded area below a curve that's revolved around the x-axis or the y-axis or any axis for that matter through 360 degrees or 2 pi radians between x equals a and x equals b. So what the heck does that mean? Um, Here's the thing that I think is most obvious. Think of a revolving door. So if you think about that door around the axis and it keeps traveling around that axis, that rectangle traveling around that axis ends up making a cylinder, right? Because that's what the inside of a revolving door looks like, right? So that's basically what we're looking at. So let me show you an example of something that might help. So let's say that we have this line right here. So as you can see, we can take that line and spin it around the x-axis, and then it makes this cone right here. So that cone is my solid of revolution. So the majority of solids of revolution that we find are going to be like this. And we're going to find the volume of these things by cutting it up into a bunch of little discs and then adding the volume of all of those little discs together, all the little tiny cylinders all together, right? Okay, so what you might have noticed back in my notes is that I said there are two methods to solve. There's the disc method when there isn't a hole, and there's the washer method when there is a hole. So there's several different methods of how to find the volumes of solids of revolution. For IBSL, we only do the disc method. We do not need to do the washer method. There's a shell method. Sometimes a function is spun around the y-axis instead of the x-axis. There's a lot of different things that could happen here. We're just not looking at those. So you could see those in a math class up ahead if you decided to keep on with some calculus. So what other things I'm talking about when it says disc doesn't have a hole, washer does have a hole. So first of all, what's a disc? So here's something you might not have known. A circle is just the outside stuff. So like a plate is not a circle. A plate is a disc. What is a circle? Did you ever have one of those frisbees that like had the hole in the middle? Okay, so like a donut, something like that. That's actually a circle. It's just the outside stuff. The stuff that's on the inside is what makes it a disc. So all of our problems are going to be these different sizes of discs that we're going to find the volumes of and then add them all together. A washer, what they're talking about is a washer like in hardware, where it's a little metal where it's a ring on the inside with a small little hole in the middle. Sometimes your function, when it gets spun around, doesn't make a solid disc. Sometimes it has a hole in the middle and looks a little bit like a donut. So here's what that looks like. Oh, restore. There we go. Okay. So right here, see, it'll kind of show them taking that graph and cutting it up into pieces. And then there's one piece that they will then take and rotate about the x-axis right there. So if you notice, it's going to keep on going around and it's going to make a ring, and that's our washer. So then that's just one partition. It will take, several partitions and add the volumes of all of those washers together to get the volume of the whole thing. Something else called the shell method is something that you see sometimes. This is when we rotate a function around the y-axis. So this time they'll cut those partitions vertically, and then they'll spin it around the y-axis. So it looks a lot like the washer method, just it's spun around the y-axis. So, like I said, we're only going to look at the disk method for IBSL 2. So, how do we find the volume of a solid that is revolved around an axis using the disk method? So, from x equals a to x equals b, that integral, I want pi times the function squared. So why would I want to do that? So remember, what we're trying to find is we're trying to find the area of the inside of that disk, right? And then we'll take all of those areas and each of those heights and take each of those little cylinders and add them all up to get that volume of our solid. So if you think about it, each of those is a circle, right? So to find the area of that circle, I have to do pi times the radius squared. Well, as we saw with that graph a second ago, when you saw like the line, that radius of our cone was wherever my function was at that time. So instead of having our radius, we have our function in there. Okay, so first thing, we want to use integration to find the volume of the solid generated when the line y equals x for x is less than or equal, or 1 is x less than or equal to x is less than or equal to 4 is revolved through 2 pi around the x-axis. So the best thing to do is first graph it. So we first want to graph the line y equals x. So my y-intercept is at 0, and my slope tells me to go up 1 over 1. Okay, so I only want to have from 1 till 4. So right here, cut it off. That's a little wonky. Here's what I'm going to do. I'm going to reflect it over. There we go. There we go. That's at 1. And then 1, 2, 3, 4. All right. I hope that kind of makes sense. If you saw that spin around, trying to make it look at least kind of round-ish to the best of my abilities. Hopefully that looks like, to me it looks like one of those cones that a cheerleader yells into or a yell leader yells into, one of those. That's what I think that looks like. So we want to find the volume of this thing. So let's first go ahead and set up an integral and figure out what the volume of this thing is. And then what I want to do is I want to go through and find the volume of it using geometry, because I think it's kind of fun to see, like, wow, that really does work. That's neat. So first of all, we know we're going to want the integral from, and then I want my first x value is going to be there at 1 until the x value there at 4. And then I'm supposed to take pi times whatever my function is, and my function here is just x. Square my function dx. So let's go ahead and solve this. So remember, we can pop the pi out front, and now I have the integral from 1 to 4 of x squared dx. So remember, I need to add 1 to the power, divide by the new power, and then I still had to multiply that guy by pi. And I need to evaluate that from 1 till 4. So the first thing we have to do is plug in 4. So I'll take 4 cubed divided by 3 minus 1 cubed divided by 3. So let's see, 4 times 4 is 16, 16 times 4 is 64. So right now we've got 64 thirds minus 1/3. 64 thirds minus, oh, and then we got pi's on all of those, don't we? Oopsies, I forgot about my pi's, I'm so sorry. So we got a 64 pi over 3, and then a pi over 3. So 64 pi over 3 minus 1 pi over 3 is 63 pi over 3. Or if we simplify that down even more, that is 21 pi. And that will be units cubed. So if we were to work this guy out with geometry, would it end up being the same thing? Absolutely. So let's go ahead and talk about how do we find the volume of a cone. We find the volume of a cone by taking the area of the base times the height and divide it by 3, just like any other sort of pyramid guy. Here, the area of the base is a circle, so we have pi r squared times the height divided by 3. So what we'll do is we'll find the volume of this big cone from 0 till 4, and then we will subtract out that other cone that got cut off right here. So if we think about this large cone, the radius right here at 4 is going to be equal to 4. The reason for that is your graph is y equals x. So that means if I'm at x equals 4, then I'm also at y equals 4. So I know my radius there is going to be 4. The height of that cone from here to here is 4. And then that's divided by 3. Well, 4 squared times 4 is the same thing as 4 cubed, so that's really the same thing right there. Same idea with this little cone right there that we would have to cut off the top with. The radius there is 1. We would have to have that squared times the height of that cone is 1 divided by 3. So 1 squared times 1 is the same thing as 1 cubed. So we would end up with the same answer either way. So pretty nifty, right? All right, cool. Anyways. Now we want to find the volume of the solid formed when the graph f of x equals x squared for 0 is less than or equal to x is less than or equal to 5 is revolved 2 pi about the x-axis. So right now, since I'm just going to go whole hog into some integration, I'm not going to be too terribly worried about what this graph looks like. I just want to get a general idea of what's going on. So I know with x squared, that makes a parabola. And like I said, I'm not trying to draw it to scale. I'm not going to go over 5 up 25 and make sure that I just don't care enough. You know how I feel. Okay. Anyways. Woo! There's my graph. Okay? Yay. There's x squared. So now we want to revolve from 0 to 1, 2, 3, 4, 5. It's right here. Okay, cool. Gotta reflect that guy over, make sure it looks right. Woo! All right. Cool. That's what it kind of looks like, a little bit like a trumpet, maybe. You know, something that kind of comes to a point. This one is not really like a shape that we were able to find the volume of in geometry. So we wouldn't just be able to default back to, let's just find some volume of cones and move on with our life, right? Calculus is supposed to help us do more things than what we knew before. So now we're going to find the volume of this guy right here. So let's go ahead and take our integral from my first x value is 0 until my last x value is 5 pi. And then I have to take my function, which is x squared, and square that. dx. Now for this problem, it doesn't matter a whole heck of a lot when I say x squared, we know what's going to happen there. Nothing is going to get messed up if we have a little bit of issues, but just remember that when you square something, that means it's multiplied by itself. So if you have like a binomial or something like that, you need to multiply it out. You can't just square each piece. Okay, so remember that for the future. Okay, cool, moving on. So right here I got x squared, so that means I have x to the 4th. And I'm going to pop that pi out front so that way he doesn't scare me. 0, 5. I have x to the 4th dx. So the next thing I'll do is go ahead and integrate. So now I have x to the, add 1 to the power, divide by the new power. So x to the 5th divided by 5. Remember, you're still multiplying that guy by pi as well. And then we want to evaluate from 0 till 5. So the first thing we have to do is plug in 5 there. So I'll have 5 to the 5th power pi divided by 5 minus. And then if I plug in 0 right here, 0 to any power is 0. 0 times pi divided by 5, 0. Okay. Now, quick thinking makes me realize that 5 to the 5th divided by 5, or 5 to the 1st, and we need to subtract those powers. I really right now have 5 to the 4th pi units cubed. And if you don't actually want to go through and leave it as 5 to the 4th, I understand. That's the same as 625. Good deal. Okay, last one. Now we want to find the volume of the solid rotating the region bounded by f of x equals 3x minus x squared and the x-axis. So the first thing we want to do is go ahead and graph this guy out. So let's hop on Desmos real quick and take a look at what that would look like. 3x minus x squared. Cool. So right now we can see that it's making a little hill over there on top of my x-axis, and it says it only wants me to find the volume formed by this curve and the x-axis. So really they're talking about this little part right here getting spun around. So it'll kind of look maybe a little bit like an egg-ish sort of thing. What is it called? And it's ellipse with oid at the end, but I'm not quite sure how to say it. Anyways, football. Cool. Anyways, it's going to get spun around that part. So let's take a look at this. First of all, we could factor this, set this guy equal to 0, factor out an x, set each part equal to 0. Or we can see from our graph that we go through the x-axis at 0 and at 3. So real quick, I'm going to graph this out. Just a rough idea of what that thing looks like. Doesn't have to be perfect. Okay. And then we are taking this and spinning it around. Ooh. I don't know how to make that look. Does that make it look rounder? Does that make it look weirder? I don't. You're picking up what I'm putting down. You just, Okay. So anyways, we know that I want to go from 0 until 3 with this integral. And then we've got that pi. And then we're supposed to take our function, 3x minus x squared, and square it. dx. Good deal. So what I like to do is, honestly, I don't want to go through and multiply that out and go through all of that work when I know I'll use a calculator to plug stuff in here in a little bit anyways. So I might as well go ahead and use my calculator. So what I would encourage you to do right now is get out your calculator, which I need to go do, so hang on. Okay, so now we want to go ahead and put this in on our calculator. So remember, it might be helpful to just go to math and then 9 to get to that integral. And we want from 0 until 3. Okay, so 2 conversations. Number 1, the pi. So your calculator will just multiply everything by pi and thus give you a big irrational number. A lot of times they're going to want an exact value and just have you pop pi at the end. So remember in that last problem, or the last few problems that we did, that pi just kind of came along with everything, right? So when we had, that pi got multiplied on after we took the integral, I had something pi minus something pi, so my answer was in terms of pi. So what I can do is just pop that pi out for right now, ignore it, and pop it back on for my answer. Just don't forget about him, okay? So what I'm going to do is just put 3x minus x squared, parentheses, squared. So my advice, definitely put parentheses inside of parentheses right there, okay? Otherwise, it might take that integral and square it. I wouldn't doubt if you got a syntax error if you tried to put a squared outside of there. I would just say, hey, slap some parentheses on there and hope for good luck. And then little dx and press enter. And we end up with 8.1. So my answer is 8.1 pi units cubed. All right. I'll see you in a few days for the little wrap up to our integration unit. I miss you guys.